Okay, gentlemen, some of you had asked some questions about how to draw the schematic for the Mousetrap car. And so I figured I would spend a little time doing that. I'm actually going to draw it off screen. I'll just pause it and draw it. But you'll be able to refer to this and I'll kind of show you what it is that I want you to do and all that stuff. All right, so here it is. All right, so here's an imaginary Mousetrap car schematic, right? So I've just, made up some imaginary dimensions, made up an imaginary car. Okay, for this particular imaginary car, these were CD wheels, so if you have old CDs or, whatever, PlayStation games or whatever, then that you might use that. I just made up an axle diameter of 0.5 inches. And then, and I don't have a mousetrap in front of me, so I wasn't able to measure one. But 2 inches is probably pretty close to what the bail on the mousetrap is going to be. I don't really know that for sure. Anyway, you can measure that. And then I just imagined that I had one with 3-inch long extender. All right, so this would be more or less what I would expect your schematic to look like. You could also do it overhead view if you prefer that to the side view. I kind of like the side view, but it's kind of up to you. Okay, I would expect your actual measurements to be real and not be made up in the way that I made these up, right? I just kind of I don't have a mousetrap car in front of me. And it's Easter break, so you guys are probably, I don't know. Anyway, I don't have the mousetrap car in front of me. Or a mousetrap, okay. All right, so once you do that, I'm not going to draw on this and screw it up a little bit, so just bear with me here. What we want to drive at is we want to get the ideal mechanical advantage of this sucker. Okay, so the ideal mechanical advantage, okay, which is defined as the, I'll call it like the length of the input divided by the length of the output. Okay, so in this case, your input is the mousetrap, right? This is the trap. Okay, and then the output is is essentially the wheel pushing on the ground. So in other words, it's kind of the total. So that total distance will be the length you travel, excluding any coasting, right? Because anyway, so this is typically how you might calculate it. I'm going to follow the Rover method here, and I'm going to show you kind of like the simplified way that we do this. I'll do this in a different color. I'll do this in red so it doesn't. Okay, so my input length, okay, is going to be basically the distance that this input force is going to be applied over, right? So, I mean, obviously that should be a perfect circle, but again, I'm just kind of sketching this at this point, so it doesn't have to be entirely perfect. I don't expect, please don't draw this on yours. Okay, but let's imagine it goes 180 degrees or pi degrees, right? So what's the arc length that that the input force is traveling? Well, remember, if you remember, the arc length is r theta. You may remember that from, was it chapter 7 or whatever it was? So in this case, the r is 2 inches and the theta is going to be pi radians. Now, I'm at pi theta, right? Pi times r, right? So r in this case is 2 inches. Okay, so you might say to yourself, well, but that's not exactly 180 degrees. Looks like a little bit long. I'm going to show you why that doesn't matter in a second. Okay, so then what we'll do is we'll go, okay, cool, that's fine. So we're going to, put that over. And what's the output? Well, the output of this first force, or this first machine, is right there, right? And it is a different r. Let's call it capital R times theta. Notice the capital R in this case is 5 inches. So I go pi times 5 inches. Okay, so I think if you look at that, you'll see right off the bat why the angle itself doesn't matter because it goes into a fraction. So these pi's are going to cancel right out, right, if I wanted to do that, okay? All right, so anyway, so now we've got the length of this output is going to be pi times 5 inches, so what's that, like 15 inches, right? So when this thing has gone approximately, 6.28 inches, this one on the outside will have gone, 5 pi, what's that, like, about 15.7 inches. Okay, so now we've got that output. Okay, cool. So now this 15.7, I want you to consider how that keeps moving on. So we're going to move into this wheel, right? And so I'm going to scroll in on this wheel right here. And I want you to imagine I've got 15.7 inches wrapped around here, right? Okay, so that's going to unwrap 15.7 inches this way. Okay, as it does, well, how much is the car going to move, right? Because the car is going to move based on this wheel. It doesn't care what the axle is doing. It cares what this wheel is doing, right? Okay, so how do we get at that, right? So for every inch that this thing moves, okay, or whatever, for every inch that this thing goes around here, right, this one is going to move proportionally farther based on either its radius or its diameter, right? So I think most of you are going to be more comfortable working with radii than diameters, so I'll go ahead and cut both of these in half. Okay, so to get the radius of the small wheel, which will be 0.25 inches, and the radius of the big wheel, which will be 2.375 inches. Okay, and I'll note, okay, so, because that's going to kind of get at, well, how much proportionally longer this is than this, right? I could have used diameters, it's fine. Okay, but I can say here that for every inch the little wheel moves, comma, the edge of the big wheel, I guess I'd say the edge of the little wheel, the edge of the big wheel moves proportionally farther. Okay, so now how much proportionally, right? So for every quarter of an inch this one moves, right, this one's going to move 2.375 inches, right? So if this one moves, let's maybe if I could do this in like a blue or something, right? Let's make it kind of like a nice thick color here. Okay, so if this thing moves a quarter of an inch here, okay, whatever radius is, says 57.1 degrees, right? So imagine we've moved this, right? If this one moves 0.25 inches, and this one will move 2.375 inches, right? So there's your ratio right there. Okay, so for every 0.25 inches the little wheel moves, the edge of the big wheel moves by 2.375 inches, okay? Which means we no longer need this statement, right? Okay, so there's my in and my out right there, right? Okay, those are my ins and my outs, okay? So it's just kind of a second machine put on top of the first one. Okay, so if I scroll out, and I'm gonna go ahead and multiply that by this one. So go 0.25 inches, we need inches here. Well, let's not, screw that up. 0.25 inches divided by 2.375 inches. Okay, and if I multiply all of those out, I get, well, and here's the thing. If I did this in a fraction, I mean in a decimal, which is much more standard for this class, okay, let's see, I'm getting 0.0421 whatever, right? Okay, notice it's unitless. If you do it right, if you do it wrong, this should never have units. Okay, that means that these numbers have all kind of canceled each other, all the units. Okay, so this is unitless. So what does this tell me, right? What does it tell me? It tells me a few things. Okay, first of all, for every inch the car moves, the bale, okay, remember the bale is this thing right here, right? It's this part of the mousetrap, so I'm talking about this particular end of it, moves 0.0421 inches. Okay, so that's interesting. Now, this could be very useful, right? If you're designing a car and you want it to go 20 feet exactly, because you can do a little math, and you can figure out exactly like a very good starting point for how long you want the lever, how long you want this to be, or how big or how small you want this to be, or how big you want the wheel to be, or like whatever, the things you can change, right? And so that's pretty cool. But there's something else that that comes into this, and this comes into the fact that this is the ideal mechanical advantage. So this also tells you about what it does to the force. So the force out, the force you get out of the car. Okay, so in this case, if this is your car, right, this is the force that the car pushes backwards on the ground, right? So here's your car, right? So this will be the force out equals the mechanical advantage times the force in. The force in is, what is the mousetrap pulling with right here? So this is the force in, okay? So if the car were 100% ideal and it had no friction or anything like that, if ideal, then IMA equals MA. So basically we could say, oh, look, it's going to take your force, your input force, which we know is really strong, right? You've felt it, like you pulled on that mousetrap car and you felt it yank on that input. Like you felt how strong it is. Well, we're going to put it through two machines, and what it's going to push back with is going to be about 4%, so 0.0421 times whatever this really strong force is. And what's going to come out will be fairly weak, okay? So the net effect here is that your car is going to go far, slowly, and so that's the idea, okay? Now, I'm going to note the other way that we can use this number. I prefer to think of this, whoa, I did not mean to do all that. I'm going to prefer to put this number in a, like a really weird, improper fraction sort of thing, which is 1 over 23.75. Okay, just because I think this is a little bit more telling than that 4% number. Okay, so this tells me that for every inch or foot or whatever, okay, the bale moves, comma, the car moves 23.75 inches or feet if you prefer. Okay, whatever unit you want, that doesn't really matter. Okay, so you might be like, well, how is that useful to me? Well, you might say, I want to go 20 feet, right? So let's start with how far does the bale move, okay? So let's go back over here. Here's the bale. It looks like the bale is going to move approximately 6.28 inches. Okay, so the bale is going to go 6.28 inches. And I want to know how far is the car going to go when the bale moves from position here to position there, right? I want to know how far that is, okay? All right, cool. All right, well, that's pretty straightforward. For every inch the bale moves, the car moves 23.5 inches. So I'm just going to multiply times that ratio, 1 over 23.75. Okay, give me the total number of inches, right? So this is going to be 149.15 inches. And let's go ahead and convert that to feet. So we'll divide by 12. I'm going to get, 12.4 feet. Okay, which means my design, and this was just numbers I made up on whatever, is going to go 12.4 feet when the bale stops, right? So when the bale gets to here, so the bale starts here and it goes this way. When the bale gets here, I'm only going 12.4 feet, right? Then I'm going to coast. So am I going to coast the remaining 7.6 feet? Okay, well, I guess it depends on how good your car is, right? So what you can do then is you can go, oh, okay, sweet. So this design is no good, right? I don't know. Maybe I can coast that far. It takes a little bit of experimentation, but I would be a little bit concerned if this were my design. So I feel like, I want to go a little bit farther. So I might go over here and I might start playing with the things that I can change. Like I could swap out the wheels. I can use a different axle and I can change this lever arm right here. Okay. Anyway, that's the idea. Again, so, your mousetrap should not have all this, your schematic should not have all this, scribbling on it. It should be basically what we started with, 1 minute into this video. Okay, I hope this is helpful. Come see me if you have any questions. All right, hope you all are having a good break. All right.